up until this point, you've probably been working with systems of equations and how we solve them given, two systems of a system of two linear equations using the elimination method, graphing, substitution. And now we're going to take it a step further and we're going to start throwing word problems at you. And this is what you're going to see in your course or whatever you're working on. The next progression is to give you some word problems, and they'll first tell you, okay, for these ones, we're going to be using systems of linear equations. But on a test or on further quizzes or maybe your final, they're not going to explicitly tell you, hey, you know what, you got to use linear equations. They're just going to give you, a paragraph looking problem like this with a bunch of numbers, and they're going to expect you to know that we're going to have to use systems of linear equations. So let's just go ahead and dive right in. When we do systems of linear equations, we're solving for two variables, two unknowns. So first off, we need to figure out what exactly we're solving for. We can't do anything if we don't know that, right? So in this very one, Loga isn't feeling too well, and she needs some soup and juice. That should be a hint right there. And cans of soup are selling for $1.50. Gallons of juice are selling for $3. Loga spent $45 buying 25 items. So I'm going to underline all these. I like to do this, underline every quantity that you think you're going to use. And with these ones, most likely it's going to be everything. Sometimes they try and throw some stuff that you're not going to use to throw you off the track sort of sense. But with these ones, underline everything you think you're going to use. And now let's see, what are our variables? What are our two unknowns that we're solving for? We know that it's asking us at the end, assuming she only bought soup and juice, how many of each did she buy? So with this one, there's not a set variable that you have to do. Usually it makes sense. Okay, if we're doing soup, we'll call that S, right? So as soup is, S is going to be the number of soups that she bought. Cans of soup, I'm just going to write soups. So juice, we'll just say that's J. So J would be the number of gallons of soup, or I'll just write gallons of soup. Okay, so we have our two variables. Gallons of soup. Why was I saying soup? Gallons of juice. Gallons of soup. That would be interesting. Okay, so we have our two variables, S and J. Now we need two equations. If we have two unknowns, we must have two equations. That's just how it is. As you get further, and probably in this course, when we have three unknowns, we have to have three equations. Otherwise, one of them is going to be just solved in terms of the other. It's not going to have a concrete number. Okay, so I should have rephrased that. If we want to actually know what the numbers are, know what the actual values of the two unknowns are, we need two equations. Okay. And that holds true forever. If we had five unknowns that we wanted, we would need five equations, and that's a whole course unto itself called linear algebra. But for our purposes, we need two equations. So let's figure out what those are. And I'll give you a hint up here. When you're first starting out, it could be tempting and tricky, where to start. But I'll give you a hint. The cost of an item, or items, is the price, which I represent by P, times the quantity. And it makes sense. So if you bought, an iPhone for $1,000, just one of them, the price would be 1,000, quantity is 1, the cost is 1,000. If you bought two of them, it'd be 1,000 times 2, it's 2,000, right? That makes pretty good sense, right? So with this, let's try and use the same thing. We know the total cost that she spent. Loga spent $45 just on soup and juice. So let's figure out what the cost of each of those items are. The items of soup, we know we don't have an explicit, an actual number. That's what we're solving for. So the price of soup is $1.50, and the quantity is what? The quantity is S. We don't know it, but we're going to solve for it. So 1.5, that looks like a 5. Let's try that again. 1.5 S, there we go. Plus, and then what's the same thing, but for gallons of juice? We know the price, it's $3, times the quantity, represented by J. Okay, halfway there, we have half an equation. What's the other equation? And this is where this part comes in, this 25. We used all these values up here. This other one's going to come into play. If we have 25 items, right, and she only bought soup and juice, then what do you think? The total number of soups plus the total number of juices should equal 25, right? So that's just represented by S plus J. The total number of soups plus the total amount of gallons of juice, right, should equal 25. And there we go. This is a very important one because it's very popular, especially when you're first starting out, and it's going to be, you'll see it multiple times. Maybe not, with soup and juice or something like that, but the idea is the same. You get a quantity of something times the price, and then just the quantity of those two added together should equal something like that. Okay, so now we get into the fun stuff, right? We get to actually solve for these. And so I like to do the substitution method on this one. So we can solve for S. We'll say S equals, that looks like a 5 again. Sorry about that. Let's try that again. That's bad. S equals 25 minus J. Okay, and let's plug that back up in here for the previous first equation, 1.5, and instead of s, we're going to use 25 minus j plus 3j. Okay, now everything is in terms of j. That's good. That's what we want. And that equals what? 1.5 times 25. We get 37.5 minus 1.5j plus 3j. So much j's here and all this stuff. Not too bad though. Okay. And let's just, at this point, up until here, right here, you should be comfortable with solving these. If you're not, then I highly suggest you go back and look over how we solve linear equations, multi-step linear equations, okay? But from here, we're going to assume that you're all masters of solving linear equations, and we're going to subtract the 37.5, and we get 7.5 equals negative 1.5j plus 3j. If we combine those, what do we get? We get a 1.5j. There we go. So j is equal to, when we divide out the 1.5, j is just equal to 5. So we've got j. That's really good. So now we can just go ahead and take this, go all the way back up here. We could plug it into here, right? But we have such an easier problem. We can just plug it into here. Or better yet, we can plug it into here. That's what I meant to point at. Point back up to here. We know what s is in terms of j. So s is just equal to 25 minus whatever j is, and in this case, j is just 5. So s is equal to 20. And we can go back in and double check just to be sure. We know j is 5, s is 20. Those are the two problems, the two answers that we got, but we can double check right here. 1.5 times 20 for s, what do we get? We get a 30 plus 3 times 5, so 30 plus 15, we get 45. And then again, 20 plus 5 gives us 25. And there we go. So Loga bought 20 things of soup, cups of soup. We didn't really specify the number of soups. She bought 20 things of soup and 5 gallons of juice, okay? So again, the main idea, and we're going to start with this next one, the main idea when we're doing this is we need to figure out what are the variables that we're solving for, and then let's go back and look at the problem and let's set up 2 equations to solve those variables. Okay, this next problem is very important because it shows up a lot, and it's a very typical problem that you'll see when we come across these. And this, we can also, the way that we're going to solve this is one of the very similar ways that we'll solve the ones that you've probably heard of. 2 trains are heading in the same direction, or maybe they're heading in opposite directions. We're going to use the same idea. But what we first need to know is this very important formula up here. Distance equals rate times time. This, at very first glance, it doesn't make perfect sense, but when you think about it logically, if my rate is 60 miles an hour and I'm traveling for an hour, how far have I gone? I've gone 60 miles. That's the distance, right? That's the main idea behind these, and that's what we're going to use. So first, let's pluck what we need to know, and let's find out what our variables are. So what are we solving for? At the very end, it's very convenient. It says, well, how fast is the current of the river? What is the boat's speed? So that's what we're looking for. And for this, let's say for current, the current of the river is going to be c. So c is equal to the current. And then for the speed, for the boat speed, I'll use b. We could have used s, but I'm just going to switch it up. Why not? So we've got our 2 variables, our 2 unknowns. Now we need 2 equations to solve those unknowns. So now we go back and look and see what we can find. So this riverboat traveled 180 miles. Okay, so the distance is 180. And when they say that, it says it traveled downstream in 9 hours. So downstream, it means it went with the current. So the current was helping it off. Okay, it was helping it along, pushing it further, pushing it faster. That's what I meant to say. So 180. The rate, what would the rate be? Does it make sense that the rate would be the speed of the boat plus whatever current is helping pushing it along, right? To help to push the boat as well. So B plus C would be the rate. The time it took would just be 9 hours, okay? So there's our first our first equation right there. Now for the second one, it's still, if you look at this, it took the riverboat, the same one, 22.5 hours to return to its original location. And when they mean that, when they say to return, we're assuming it went upstream, it went back upstream. There wasn't like some side route that, somehow defied, we didn't have to go, it's kind of going downhill both ways type of thing. We're going to assume that it went uphill the other way around. Now with that, now think of it, it's going against. If it's going against the current, it can't be B plus C because it's making it slower, right? If I'm going against the current, it's definitely not going to help me, right? So in this case, it would be B minus C would be our rate, and then the time it took would be 22.5. And these quantities right here for the time make sense. If I'm being helped along by the current, it should take less time than if some current is pushing against me, okay? So now we've got our 2 equations, and it's up to you how we solve them. I preferably, I'd like to use this one right here, but you're more than welcome to use this one down here. And for this top one, what can we do to both sides to make things easier? Can we divide something out? You're absolutely right if you said we could, because we can divide both sides by 9, and we get 20 equals B plus C. Let's solve for B just because, and we'll get B is equal to 20 minus C. So we've got one variable in terms of the other. That's a good thing. Now we can go back in and plug in. We go back and plug it in down here for this other equation. We'll get 180 equals, instead of B, we already know what B is now. It's 20 minus C, and then minus that C that's right there, all in parentheses, times 22.5. So we'll come back. Let's do a little simplification. Again, I like to use the division rule because we can get rid of this 22.5. It might not seem obvious at first, but if you double 22.5, that becomes 45. 45, if you double that, that becomes 90. And we know there's two 90s and 180. So if we divide both of these by both sides by 22.5, we should get, oh, let's try that again. We should get 8. We should get 8 is equal to, and then if you simplify what's in here, we get a 20 minus 2C. Okay, so now let's simplify this. And again, if you're not sure what we're doing here, then I highly suggest you go back and see how we solve linear equations, okay, how we simplify linear equations. So with this, when we subtract 20 from both sides, we should get a negative, what? We should get a negative 12 equals negative 2C. C is just equal to 6. So the current of this river is 6 miles per hour, okay? So we've got C, and we already know an equation of that relates B and C. It's right here. B is equal to 20 minus C. So again, we could plug it back into either one of these and we'll get the right answer. But why do that? You know, work smarter, not harder. My favorite phrase. So we know what C is. Let's go ahead and plug in for B. We get 20 minus 6. B is equal to 14. And there we go. And if you wanted to go back in and plug in and see if we got it right, well, B and 6, so 14 plus 6 is 20, times 9 gives us 180, and 14 minus 6 gives us 8. 8 times 22.5 is also 180. And there we go. So the speed of the current is 6 miles per hour. The speed of our riverboat is 14 miles per hour. And again, this is a very important one. The D equals R times T. The distance is rate times time. That's a very important one. We're going to use that a lot. And you'll see that. I don't want to say a lot, but it'll be prevalent, okay? And there's different methods. I'm going to make a whole different video solely based on the different variations of that we use. Okay, so for this last one, it's very similar to the first one, but it's a little bit different. So we've got Abigail and Kat, and they're selling raffle tickets. One of them is adult, one of them is for children. Both of them are probably going to be different prices, right? So it tells us how much Abigail brought in, selling X amount of this tickets, this amount of this tickets. Kat with the same thing. She made this amount, selling this amount, and this amount. All these different amounts, right? So basically, now we want to go through this and see what are we solving for. That's the first step. What are we solving for? We want to know the cost of a child's ticket and the cost of an adult's ticket. So we can represent those again. We can put whatever variable we want, but it makes sense that C would be the child's ticket, the cost for the child's ticket. So cost for the child's ticket, and then for adults, we might as well just put A. I'll put a lowercase a because in the variable or in the equation it'll look a little bit better. A is the same thing, cost of adults, and I'm just going to freehand this adults ticket. So now we've got our two unknowns, and now we need two equations to solve those unknowns, just like the other two. What can we get? Well, let's look at what Abigail did. She brought in $64, right? Selling 6 child tickets and 4 adult tickets. And if you remember, the cost is equal to the price times the quantity. That's also, I don't know if I wrote that up top. I think I did, but if I didn't, this is also, that's a very important one, okay, for these, especially for these word problems that we're going to look at. So cost is equal to price times quantity. Well, we know what the quantity is. She sold 6 child's tickets. And what's the cost? The cost is C. We don't know what it is explicitly yet. We don't have a numerical value for it, obviously, because we're trying to solve for it, but we're going to put that there. So 6C. Now, what about the adult tickets? We know that she sold 4. So the quantity is 4, and then the price is just A. The price is just A. And I should have put, I put the cost on here. It's probably confusing. Why do you have cost up here, cost on here? I probably should have put price for this, okay? So with this, that's the first one. We've got one equation. We're looking good. Now let's see what we get with the same thing down here. If we can do the same, apply the same method to what Kat did. So Kat sold $52 worth. Well, why did I put 54? She sold 52. So $52 worth of 8 child tickets. So we know the quantity is 8, the price is C, and then 2 adult tickets. So 2 of those at a rate of $8 per ticket. So now we've got our 2 unknowns. Now how do you want to solve this? We can do substitution. If you notice, the other one that we subbed for when we did the previous problem, there was one basic one that was pretty easy to solve for. In this particular one, we can solve for it with substitution. I'm just going to personally do elimination, but you're more than welcome to go ahead and try substitution if you'd like. If you want to go ahead and try and graphing it, why not? But with this, when we do this, we'll end up with, I'll write the first one first, just down here. So we'll get 64, that first expression, that's not going to change, plus 4a. 6c plus 4a, that's a c. C. And then what does this become? This becomes negative 104. Negative 104 equals, and remember, when we're doing this, we're multiplying. If you don't remember how to do elimination, we're just trying to change one so that we can eliminate one of the variables when we add them up. So we're negative 2 times 52, negative 2 times 8c, which gives us a negative 16c, and then negative 2 times 2a, and we get minus 4a. Now we're going to see what we get when we add those. And when we do, luckily, this is literally why they call it elimination. We just eliminated one of the variables. Now we can rewrite it in terms of one variable. So we get negative 10c equals, what is 64 minus 104? It's the same thing as 104 minus 64, just negative. So we get negative 40. And we solve that, and we get C is equal to 4. So we've got C. The cost of one child's ticket is $4. Okay. And the only thing that's different, when we didn't substitute, we didn't come up with an explicit value for one of the variables solved in terms of the other variable. So, but that's not a big deal. We can just go back in and let's say we pick this first one. So we have 64 equals 6 times c, and we know what c is. C is just 4. So 6 times 4, and actually, you know what? I'm just going to go ahead and simplify that. 6 times 4 is just 24 plus 4a. And now we subtract both of these. We get 40 is equal to 4a. Again, I'm blowing through these steps because I'm assuming that you're comfortable with solving linear equations. And if you're not comfortable with solving linear equations, again, I highly suggest you go back and get comfortable with that, because it makes sense that you would know how to do these if you're doing systems of linear equations. Otherwise, it would just be madness and a bunch of guessing and probably hair pulling out, and just it would be very unpleasant. So, but there we go. When we get that, we've got there's the $4 per child's ticket, $10 per adult ticket. And again, we can go back in and see if we got the right answer. With all of these, I think I recommend this in, I want to say at least every video if we can, but go back in and plug in your values and see if you have time and see if you got it right, especially on a homework, or a quiz or a test, something like that. But up here, what's 6 times 4? We get 24 plus 4 times 10. So 24 plus 40, that's 64. Okay, we're looking good. And when you plug it back in, you don't have to do this times -2 on the bottom. Let me get rid of that. So if we look at down here, 52 equals, so 8 times 4, so that's 32, plus 2 times 10. So we have 30, what I said 34, I meant to say 32, excuse me. 32 plus 10, and that plus 10 plus 20, excuse me, oh my goodness. Plus 20 is equal to 52. And there we go. So the cost of one child's ticket is $4. The cost of an adult ticket is $10. I highly recommend you go back and plug in your values and just double check and make sure, because then you can catch yourself and you'll know right up front, hey, did I get this right? Did I get it wrong? Let me go back and double check. So that's the main idea behind the basics of these solving systems of linear equations in word problem form. Again, I want you to be comfortable with how we do these, because again, they're not going to tell you, like I did here. I explicitly said, if you looked at the title of the video, word problems using systems of linear equations or something like that, but they're not going to tell you that. They're just going to give you this paragraph and expect you to understand it. And you'll probably see it. If we have all this stuff and we're solving for two different things, soup and juice, I have to have two equations. Oh, wait, Justin said systems of linear equations. Okay, that's going to be fun, right? But that's the main idea behind these. Figure out what you're solving for. What are your two variables? And then go back, find your numbers that you actually used and create two equations, and then go about how you solve them using either probably the two methods. You're not going to graph it. There's no point in making this and figuring out where goes what and where, So that's pretty much what we do for these ones. And in future videos, we'll take it a step further with some trickier looking ones. And then I'll dedicate a whole video to the distance equals rate times time, because there's multiple different variations of that. All that fun stuff. I hope you found this video helpful. And until next time, this is Justin with Top Tier Math.